All right, recording, re-rolling. We're back where we left off on the posters. So this is Unit 4 by AP's book. We're doing energy. Energy can take lots of different forms. These are the forms you care about for this class, forms of mechanical energy. I don't have up here chemical energy, thermal energy. Okay, but we've got work as force times distance. That's an energy transfer. We've got energy potential, gravitation potential energy. Right? If you lift something some height, put it on a shelf. Right? No, actually, this green line right here, universal potential energy. Don't worry about that so much. I highly doubt AP is going to ask anything like that. You'll see a poster about this later, right? This one is if this gravity field is not constant. So if you're like sending a rocket to the moon, maybe you have to care about the universal form, right? Energy stored in a spring, 1/2 kx squared. Guys, don't mix that one up with the other spring formula you guys know. Force equals kx. That's Hooke's law. Force equals kx. Energy is 1/2 kx squared stored in a spring. K is the spring constant. X is how much it's either stretched or compressed. Energy in motion, kinetic energy, 1/2 mv squared. And if something's rolling, rotating, well, there's also energy associated with rotating. That's 1/2 I omega squared. Right, you guys get there? Forms of mechanical energy. Right, you want to know those, and then maybe you don't have to study this universal potential energy as much because that one's not going to show up in the exam. All right, so force times distance. Well, it's actually force dot distance. That dot product means you only multiply the parallel components. For example, if you lift an object up the stairs, only the height change counts, not the lateral movement. And if you push a shopping cart, only the forward component of your push actually counts because the shopping cart moves forward. So trying to consider how many joules of energy are transferred. Right? That's what work is. Right? Guys, this graph right here, force versus distance graph, you're gonna see probably multiple versions of this graph show up on the AP exam, right? Whenever you see force versus distance, look for an energy or work question, like how much work was done on the object or the system, how much energy was transferred. And the answer is always just the area underneath the curve, because force times distance, right? If you have a constant force, then it's gonna be a rectangle shape. It might possibly be some other shape, but I have a rectangle shape, right? Constant force. Work as force times distance. All right, closed and open systems. AP might ask you a question like, what does that mean to be closed or open? So here I've got the sum of energy initial equals the sum of energy final. Energy is conserved. You could say there's no energy entering or leaving the system. If there was, then that would bring it to open system. If there was work done on or by the system, now you got energy entering or leaving the system, right? And that goes hand in hand with maybe there's some external force for some distance. That's how you get work, right? Okay. Right, here's a classic closed system. Guys, what is in the closed system? The ball and the Earth. There's the ball Earth system. Galileo drops the ball. How fast is the crash speed? Well, here's one way to solve it. Energy is conserved. It's all potential energy at the top. It's all kinetic at the bottom. The mass of the ball cancels out. The answer is always square root 2gh, as long as he drops it, right? Square root 2gh, right? You guys have probably seen that at least a dozen times, right? Okay. Hey, what if you go the other way? The other opposite side of the coin. What if you throw a ball straight up? How high can you throw the ball based on throwing speed, right? Okay, so you can do conservation of energy just backwards of the Galileo question from last poster, right? Here's the maximum height based on throwing speed. Or what if you know how high it goes and hey, I wonder how fast I threw it straight up. Well, that's the line right beneath it. Hey, look at that. The throwing speed now is square root 2gh, right? It's just the reverse, right? You might be thinking, wait, couldn't I have solved this with kinematic motion? True, you could have done it with kinematic. It's a different setup, but it leads to the exact same outcomes. Right? Get that too. Right, there you go. Height, speed, there's a relationship. How about a block spring Earth system? I like this one because it involves 3 different forms of mechanical energy, right? Let's say there's no friction. So story, we're going to press this mass against the spring. Now we've got some energy stored in the spring, 1/2 kx squared. Maybe that's like 100 joules, for example, right? Then let it go. Pew! It's going to fly around this loop. Maybe I want to know how fast it's going to the top. All right, well, by the time it gets to the top, the energy went to 2 places, lifting against gravity and giving it some speed, right? So we got potential energy, kinetic energy. Maybe you run the calculation, get like 70 joules went to potential energy. That leaves the other 30 joules for kinetic energy. 100 equals 70 plus 30, right? Notice it's joules equals joules plus joules, right? I can't mix and match different types of units. Like I can't say, force equals kx and have kx here, because that wouldn't make any sense, right? It has to be joules equals joules plus, yeah, thank you. Right. You guys see how those are all energy terms, right? Have to be all energy terms. Right? roller coaster minimum height, like what minimum height do I have to drop this to make sure it gets around? You guys saw a bowling ball version of this, right? So this is like a two-part question. First, you have to figure out, well, how fast does it have to go to get around? That you saw yesterday. The minimum speed here is square root of GR, right? So here, I almost got that one, right? Then you kick back to conservation of energy. Well, it has all potential energy at the top of this hill. See, maybe it's okay. Had to climb this wall, this vertical wall, so there's some potential energy there, and the leftover is kinetic. Anyway, there's this whole proof at the end of the day. The minimum height drop is 2.5 times the radius. So 1, 2.5 here, right? Has to be that higher. That could be an FRQ. I bet that could be an FRQ right there. Right? A little complex one, but yeah. Right. Ooh, pendulum maximum speed. What's the speed of the pendulum at the bottom? Oh, the speed of the bottom is square root 2gh, just like the Galileo question, right? But I mean, we've got an extra couple of complexities here. You could figure out what is that height drop based on the length of the pendulum and the starting angle from the vertical. It's a little bit of extra geometry. So instead of square root 2gh, we'll say square root 2g, and then h becomes this whole expression, L1 minus cosine theta, right? You should be able to derive that. This would be a pretty solid FRQ. I bet AP could ask this as an FRQ, right? One more twist. If you drop it, like release it from rest, it's just all the black ink. But what if you give it a push? If you give it a push, you also have to consider this gray ink, right? Maybe it starts off also with some additional kinetic energy. And here's how it translates to the end, right? Okay. You guys should be able to solve this whole thing from scratch for AP, right? Oh, you guys did a lab version of this. Remember, I had you guys do the calculation and then take a speed gate and say what was the actual empirically measured speed. Say, hey, same. Right? Oh, car brakes to a stop. How many times have I brought up this example, right? Here's a classic open system. The car starts off with all kinetic energy. Energy is leaving the system that consists of only the car, force times distance, friction force times distance, subtract that out, ends up with 0 mechanical energy at the end, right? So what is the braking distance as a function of the initial speed of the car? Here's the full equation answer right here. Got coefficient of friction, gravity field. Okay? And what I usually focus on is this proportional relationship between these two variables, and I pull that over here as a proportion, right? Braking distance as a function of initial speed. Something like that. There's a square relationship. So, guys, 3 times the initial speed of the car is how many times the braking distance? 9 times. Right, the square relationship. There you go. Good to know when you're driving. Ooh, Atwood. Now, well, hold on. We saw some Atwoods way earlier in this presentation. That was the Unit 2 dynamics section. You can get a question like, what's the acceleration as a function of the two masses, right? But that's not what you see here. Here, this is a good setup for what is the speed after it's moved some distance, h, right? Right. If you get that question, what's the speed, say the downward velocity of the large block after it's moved some height change, right? This is the fastest way to solve it. Not the only way, but the fastest way. I would say the fact that the large block can fall is supplying potential energy. That goes into 3 places. You have to lift the small block. There's that one right there. And then give each of these blocks a speed, so there's some kinetic energy for there and there. Okay, guess the energy mix, right? The other way to solve this, which would take more paper, would be, well, let's say I could solve for the acceleration of the system first, get that, right? Then kick back to kinematic motion, say after it's moved some distance with that acceleration, what's the final speed, right? Of course, you would get the same answer. Right. Ooh, there's a little bit more complex version, right? Okay. Look at that. Oh, maybe I have an open system. Maybe there's some friction up here, possibly. Okay. That orange. Mechanical advantage pulleys. You guys remember rigging up all these pulley systems? How you get a mechanical advantage? So the guiding physics principle is that work input equals work output, right? You can't amplify the amount of energy. The amount of joules is whatever it is, right? So force times distance equals force times distance, right? In and out, right? The catch is then that if you're, in this case, divvying the weight 3 ways, you can have a third of the input force. So you've effectively amplified your strength by a factor of 3, right? Now you have to pull lots and lots of string, and then the weight moves up just a little bit at a time. A 3-to-1 mechanical advantage. There's ideal, there's actual. Okay, so here's your lab table for that. You guys rigged up lots of different pulley systems. You can get mechanical advantage from wheels, from leverage, from an incline. If that box is too heavy to lift, maybe you can scoot on some wheels and like push it up this incline. Mechanical advantage, right? Here's lots of simple machines. You get mechanical advantage from all these simple machines. Right? Leverage. Ooh, this one looks kind of like your guys' seesaw lab. You guys were like balancing that kind of deal, right? Power. So the textbook version of power is work per time, right? Energy transferred per time. So the rate of energy transfer, work per time, right? Now, if you have like an elevator situation, you want to know, maybe at the top of this elevator shaft, there's a motor that's pulling up this elevator at some speed, right? How many watts is that motor drawing, right? What's the power output of that motor at the top of the shaft, right? Well, let's rearrange this formula a little bit. So work is force dot distance. Hey, distance over time, that's velocity. You could do force times velocity. So what is the tension in that cable times how fast is it being pulled up? Right, there you go. That's how many watts. Right, I can see that. Right? Now I'm showing an elevator being pulled up at constant velocity, and I know that's true because it's in equilibrium, right? The tension matches the weight, right? It could be accelerating, and if it is accelerating, then this power is only true for one instant, and it's always changing. Gravitational potential energy. Okay, now this is kind of beyond the scope of this class, but I think it's extra good to know. Here's a universal form of gravitational potential energy, negative GMM on R, right? That's if you have like a changing gravitational field, right? Now you can show for a small change in height, right? From R2 to R1, does the gravity field change? Probably not very much, right? That simplifies to just MGH, right? Which is really the one you just need to know for this class, right? Potential energy could be MGH. Right. All right, momentum. All right, now we're moving on to Unit 5 by AP's book. Momentum. Momentum is mass times velocity. See right there? We're talking about vector value. So forwards versus backwards matters, got positive versus negative direction. It's conserved in collisions. Whenever you see a collision, you're probably going to get a question that involves this right here, right? The exception is if something ever collides with the spring, then don't think about this, right? But any other kind of collision, like two blocks collide, two balls collide, like something to do with this right here, right? Closed and open system from momentum perspective. So this says momentum is conserved in a closed system, right? Right. Now, if you have an open system, you can get an impulse. So the initial momentum, I guess some of momentum, right? Plus or minus some impulse, change of momentum gives you your final momentum, right? You get an impulse from force times time interval. Right? All right, so here we go. Here's for a closed system. This is all in one dimension. We're just doing one-dimensional collisions. Right? All the mass times velocity bits before and after the collision have to equate. Right? Here's a perfectly inelastic collision. Two objects collide and stick. Right? If AP asks you, AP likes to ask these kinds of collisions because the math is pretty straightforward. Let me toggle back and forth. Here's general, inelastic, general, perfectly inelastic. Right, you guys see that? Right. Right. Perfectly inelastic, one giant mass, common final velocity. Right. Here's perfectly elastic. So system of equations, momentum is conserved, although that's true for any kind of collision, right? But also kinetic energy is conserved for this special kind of collision. Talk about like Newton's cradles, probably pretty close. It's like perfectly bouncy, right? AP tends to not ask this question, or maybe they'll ask like one question. I remember your AP classroom questions with this. The fastest way to solve it was we went through the multiple choice answers and said, well, which one does the kinetic energy equate, right? Okay. This gold box is the solution to that system of equations. I don't think you would really be expected to memorize that or know that for the AP exam, right? All right, here's a big old table, different spectrum of collisions, perfectly bouncy, perfectly sticky. I throw on an explosion down here for fun. Every single one of these, momentum is conserved, right? But there's something maybe a little bit different going on with the kinetic energy, right? Okay, collisions lab. Coefficient restitution. How bouncy is a collision? We're looking at post-collision compared to pre-collision difference in velocities. AP is not going to ask that. Right? Here's a lab version you guys did where you're like bouncing a ball off the entire Earth. Right? You can do this version of it. Right? I mean, you should be able to derive this, right? Like the crash speed is square root 2gh, right? I'm gonna have to drop it. Okay, plug in those values. Right? So you guys did that lab. How bouncy is the ball off the tile floor? Right? Bouncing on it off the Earth. Right? Impulse. All right. Now this right here, you definitely want to know. Because whenever you see a graph that's force versus time, and on the AP exam, I bet you're going to see several of those graphs, force versus time. You should immediately start thinking this has something to do with impulse or momentum, right? Because it's just the area under that curve. Suppose this bat's hitting this ball, pow, right? These graphs usually take triangle shapes because the process is, okay, they make initial contact here, push, 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 push. and then the ball maybe starts to rebound and then leaves the bat right here, right? So the area under force versus time is impulse, transfer momentum, right? You could play off average force times time interval. Do you guys see that that rectangle has the same area as that triangle? I said, right? So how about equation? Delta P, change of momentum, is the impulse. That could be mass times change of velocity. But you get that from force times time interval. Okay? All same thing. Right. So a couple of questions were these two right here, right? Right. So the bouncy collision transfers more momentum than the sticky collision, right? Something like that. Right. Oh, ballistic pendulum. So the question is usually how fast is the bullet fired to send the pendulum up to some height change, right? And it's a two-part question. You solve it backwards in time, if that's your question. So first, energy conservation. How fast did this block get swinging so that it could swing up to that height change in the first place? Hey, it's square root 2gh, right? And then you step back in time and say, well, what collision from the bullet got it moving that fast, right? So I have inelastic collision, and then you can solve for the speed of the bullet. Boom, boom, like two parts. Two-dimensional collision. If you have a collision in 2 dimensions, remember that momentum is a vector value is conserved, so it's conserved along each axis. Maybe I have one billiard ball running into another billiard ball. Momentum would be conserved along both the y and x axes, right? You could also turn this around to this, the opposite direction. For example, if you have a car collision, maybe one car is going north, one car is going east, and they collide and scoot together. Similar principle, right? All right. Well, that is as far as I've been getting today. So that is our pause point. We're getting to the purple banners up here. So we'll save the rotational dynamic slides for tomorrow, and that will take us to the weekend. Right? Yeah, guys, go look for some meteor shower tonight.